So welcome back to this next concept, and if you saw from the previous video, there's actually a small typo, okay, not series, sequence. So we are going to be discussing what exactly does it mean by convergence and divergence of an infinite sequence, okay, and we will also tackle a question later on. So just to recap from the start again, right, a sequence, what exactly is a sequence? A sequence is an ordered set of numbers, right, and this set of numbers can either be finite. So finite means there's a finite number of numbers, or it can be infinite, right, whereby the sequence never ends. So an example of a finite sequence would be one that looks like that, right? 1, 2, 3, 4, 5. And it's finite because there is only 5 terms. It can be infinite where it's 1, 2, 3, 4, 5, and then it carries on naturally. Now, so far, we have discussed about this too. So the first thing is, what exactly is the meaning of convergence and divergence? These two concepts actually come from the notion, rather the idea, right? The big picture idea is for the general term of this. Okay, so let's just put it this way. This sequence over here, the general term is un equals to n, right? Because u1 is 1, u2 is 2, and then u3 is 3. So you know that un is n. So the idea behind it is as n approaches infinity, right? And the reason why we can say that as n approaches infinity is because this is an infinite sequence. So this concept that we are talking about only applies to infinite sequences, right? It does not apply to finite sequences at all. So for finite sequences, we can ignore the concept for finite sequences. Why can we ignore this concept of finite sequences? As the n value is limited. Over here, it stops at t5. It stops there. But for infinite sequences, the n can approach infinity. And since it can approach infinity, then that is where we can actually apply this concept. Okay, so the first thing to note is that for the idea of convergence and divergence, it can only be applied to infinite sequences because only in infinite sequences can the n approach infinity. So as the n approaches infinity, for this case, my n value over here will approach infinity as well. It will also approach infinity because un equals to n. And since un also approaches infinity, this over here is what we call a divergent sequence. Now I give you another example. So suppose another sequence. Let's say I have another sequence over here, which is, let's say, for instance, 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and it goes on perpetually, right? So another infinite sequence. So we can tell that the general term this sequence is un equals to 1 over n, right? Because this is t1, t2, t3, t4, t5, and then it goes on perpetually, right? And then we see that this number matches this number, right? This number matches this number, this number matches this number matches this number matches this, right? So similarly, this will match this, right? Now, what happens to the value of un as n approaches infinity, since this is an infinite sequence? So as n approaches infinity, so imagine for this general term over here, when my n becomes very big, right, as n approaches infinity, like super big, right, this n will actually approach a specific value, which is 0. And why does it approach 0? Is because you can think of it as 1 over infinity is as good as it being 0 already, right? Because if you take 1, divide by a humongous number, right? For example, you take 1, divide by 1 trillion. The value that you get is going to be 0.000000000 all the way at 1, right? So it becomes so small to the point that it's as good as 0. But it's not exactly 0, don't get me wrong. It's almost 0. So this symbol over here, the meaning of this symbol is it approaches 0, right? So since un approaches a specific value, right, and in this case, the specific value for us is un approaches 0, this is a convergent sequence. All right, so that is the idea behind a convergence and divergence of an infinite sequence. To wrap it up, sequences got two types, either finite sequence or infinite sequence. Now, for finite sequences, you don't need to talk about the idea of convergence or divergence, because to begin with, your n value of the general term cannot approach infinity, right? We only talk about convergence and divergence when the n can approach infinity, because we are only concerned about how does the general term behave as n becomes very rich, right? So this concept is only usually brought into the picture when n can be extremely huge. Right, so we are only concerned with infinite sequences because for infinite sequences, n can be like pretty huge. Now, when n approaches infinity, looking at the general term, if it approaches infinity as well, that means it does not converge to a specific value. It also tends towards infinity, and therefore we call this a divergent sequence. On the other hand, if let's say my general term is, say, a fraction, right, something like 1 over n, as n becomes extremely huge, my general term will become extremely small because the denominator will become very huge. And as a result, the general term will tend towards 0. Not 0 exactly, but it tends towards it. Therefore, this is a convergent sequence because my sequence, you can imagine it as converging towards a specific value. Whereas for a divergent sequence, it actually converges outwards like that. And this is the idea behind a convergence and divergence of an infinite sequence. Watch this video as many times as you need to really get this concept clicked in your head. If not, we try out the next example question that we have below. Alright, so let's start to attempt this question based off the previous concept. Now, before we actually do this question, I want to also bring up this concept, which is from the previous portion, we know that when it tends towards a specific value, it's a convergent sequence, right? We say that the sequence converges. This value over here is also known as the limit of the sequence. So in other words, the value that the sequence actually converges towards, that is also known as the limit of the sequence. Okay, and with that said, then this portion of the question would make sense to you. Okay, if not, feel free to pause this video right now to actually tackle the question here. And once you're done, return back to this video. If not, let's break down this question together right now. So we have 3 general terms of 3 respective sequences, and we are asked to determine whether the sequences are convergent. So I'm going to show you the official presentation right now, and the way that you present is also a little bit different from how you would usually write it in just words, right? But in math, there's a lot of ways to present your answers, which are a lot more efficient than just writing in words. So for A, we have the answer as such. So usually in words, right, we'll write as n approaches, I'm just going to write it out in words first, as n approaches infinity, un approaches something. Now, in math, you can also write it this way. So remember, we are trying to figure out what's the limit, right? So the limit when n approaches infinity, okay? Now, when n approaches infinity of what? Of un. Okay, so the value that we get eventually would be 0, right? Why is it 0? So imagine this. Okay, so from here, we can infer the sequence. And the sequence that we can infer is that we know that the sequence is half to the power of 1, half to the power of 2, and then half to the power of 3, and then half to the power of 4, and then it goes on perpetually. And we know that it goes on perpetually because we know that the n value over here can take on any real positive integer values. So as n approaches infinity over here, right, we know that my un over here, my general term, when we have half to the power of infinity, is as good as saying you have half times half times half times half many times, right? Infinite number of times. And when you take something, divide by half, infinite number of times, you end up with something that is almost as good as 0, something that tends towards 0. So for A over here, we would say that the limit of this convergent sequence is 0, right? First and foremost, it is convergent because it tends towards a specific value. And since it tends towards a specific value, that specific value is also known as the limit. Now for B, we are given that the general term is -1 to the power of n. So if we were to visualize how the sequence actually looks like, you start with -1, then you move on to 1. Then after that, you move back to -1 because you have -1 to the power of 3. And then this goes back to 1, and then this goes back to -1, and then it just goes on perpetually, right? Because this one is -1 to the power of 1. This is -1 to the power of 2, this is -1 to the power of 3, this is -1 to the power of 4, this is -1 to the power of 5, right? And then it goes on perpetually. So you can see that the value doesn't change apart from it being 1 or -1, right? So you can see that the value, even as n approaches infinity, the value will not converge at all because it's just -1 or 1, right? It just rotates in between these two. So therefore, we will say that it's not convergent, right? And since it's not convergent, thus it does not have a limit. So we don't even need to write out the equation above because there's no limit to begin with. So yeah, that's it for B. Okay, so sometimes you might need to like sketch out the set first, figure out what's the relationship, right? What's the pattern. Now for the last one, un equals to 3 to the power of n over n factorial. So un is 3 to the power of n over n factorial. So is this convergent or not? So just a recap, what's n factorial? So n factorial is basically just n multiplied by n minus 1, right? Multiplied by n minus 2 all the way until you reach 1. So for example, let's say I have 5 factorial, right? This is just 5 times 4 times 3 times 2 times 1. So as n approaches infinity, before that, let's just sketch out the sequence to figure out how it looks like. So the first one will be 3 to the power of 1 over 1. So I'm just going to write it as 3. The next one will be 3 to the power of 2, which is 9, over 2. The next one will be 3 to the power of 3, which is 27, over 6, right? Maybe I write it in the same sequence, right? So here's 1, 3 square over 2 times 1, right? Then this is 3 to the power 3 over 3 times 2 times 1. And then here you have 3 to the power 4 over 4 times 3 times 2 times 1. And then you have 3 to the power 5 over 5 times 4 times 3 times 2 times 1, right? And then you realize that from fraction to fraction, the fraction actually becomes smaller, right? You realize the pattern. The pattern is that the fraction becomes smaller as n becomes bigger. So eventually you imagine this, right? Your n can be any positive real integer. So as n approaches positive, what happens to your generator? When you have infinite number of terms in the denominator, right? You realize that your denominator will be much larger than your numerator, because when you have infinite number of terms in the denominator, your numerator cannot match it, right? Because your numerator is just 3 to the power n, right? So the idea behind this is that since the denominator is bigger than the numerator as n approaches infinity, we know that it's a convergent sequence, because it will eventually converge to a point and tend towards 0. So we will say that for this question over here, the limit of the sequence, which is un, as n approaches infinity, would just be 0, right? And since it's a convergent sequence. Okay, yeah, so this is it for this question over here. And as you can see, it's really a lot about being sensitive to the sequence. You need to map it out first to see the relationship between all the terms. If not, that's it for this. If you have any questions, do leave it in comments below. If not, I'll see you in the next video.